We want to find all the zeros of the polynomial function given 4i as a 0. Then we want to write p of x as a product of linear factors. So for a quick review, the complex factorization theorem states that if we have a degree n polynomial function, then there are exactly n complex zeros as long as we count multiplicity. So we're going to find all the complex zeros of our given polynomial function, and then using those zeros, we can write the polynomial function as a product of linear factors, as we see here, where the r's would be the zeros, and the exponents m would be the multiplicity, and in this form, a would be the leading coefficient. So going back to our example, the first thing we should notice is that we're given 4i as a 0. So if we're keeping a list of our zeros, we know that x equals 4i is a 0, and complex zeros always come in pairs. If 0 plus 4i is a complex zero, which we're given, then the conjugate of this, 0 minus 4i, would also be a 0. So we can also make a note that x equals negative 4i would be a 0 of the degree 5 polynomial function. So now we want to find 3 more zeros so we can write the 5 linear factors that would make up this degree 5 polynomial function. To do this, we could use the rational roots theorem by making a list of possible rational zeros using a ratio of the factors of the constant term 64 over the factors of the leading coefficient 3. But instead of doing this, we're going to graph the polynomial function and look for the real rational x-intercepts, which would also be the zeros of p of x. So here's the graph of the given function. Notice how there are 3 x-intercepts. So the 3 remaining zeros are real. Notice 2 of these are pretty easy to find. Here's one x-intercept at negative 1, 0. And here's another x-intercept at 2, 0. Notice that these x values, the y value or the function value would be 0. The one we're not sure about is this one here. We probably could use our graphing calculator to determine that value, but we're going to go ahead and use the known zeros, which will give us factors of the polynomial function, and then perform division to find this remaining 0 and remaining factor. So going back to the previous slide, let's also record that x equals negative 1 and x equals 2 would be a 0 of the function, and we're still looking for one more. But because we have 4 zeros, we do have 4 linear factors that we can use to help us find the 5th factor and this 5th zero. We know now that p of x will have 5 linear factors. So starting with x equals 2, if x equals 2 is a 0, x minus 2 must be a factor. Notice how x equals 2 would make this factor equal to 0, and therefore this function value equal to 0. If x equals negative 1 is a 0, then x minus negative 1 or x plus 1 would be a factor. If x equals negative 4i is a 0, then x minus negative 4i or x plus 4i would be a 0. And if x equals 4i is a 0, x minus 4i would be a factor. So if all of these are factors of the given polynomial function, then they would divide evenly into the polynomial function, so we can perform division 1, 2, 3, 4 times, and that would give us the remaining linear factor, which will help us find this factor and the last 0. So let's begin by dividing this degree 5 polynomial by this first linear factor, x minus 2. So if we want to divide this by x minus 2, let's go ahead and use synthetic division. We'll start with the 0 of 2, and then we'll list the coefficients, which will be 3, negative 5, 44, negative 76, negative 64, and 64. Go ahead and bring down the 3 to begin, and start multiplying by 2. 2 times 3 is 6, and then we add. 2 times 1 is 2 when we add. 2 times 46 would be 92, and we add. 2 times 16 is 32, and we add. 2 times negative 32 is negative 64, and we add. Notice how the remainder is 0, and that's because x minus 2 is a factor of this polynomial function. And now we're going to go ahead and divide by the next factor of x plus 1. So if we want to divide by x plus 1, we'll actually use -1 to perform synthetic division. And we'll go ahead and use these values here, ignoring the remainder. Bring down the 3 and start multiplying by -1 this time. -1 times 3 is -3, and we add, it's -2. -1 times -2 is 2, we add, that's 48. -1 times 48 is -48. We add, that's -32. -1 times -32 is +32. We add, which is 0, which is good news. And now we have two more remaining factors that we know of, x plus 4i and x minus 4i. And we can still perform synthetic division using an imaginary number or a complex number. So let's go ahead and try it. Now we're going to divide by the quantity x plus 4i. So we'll use -4i here. It'll be a little messy, but we can still do it. Remember, the remainder here still should be 0. So we'll bring down the 3, multiply by -4i, it's -12i. When we add this, nothing simplifies, so we have -2 minus 12i. We're going to multiply this by -4i. Let's multiply the two I terms first. -4i times -12i would be 48i squared, or -48. And then we have -4i times -2i, that's plus 8i. When we add here, those are opposites, so we're left with 8i. When we multiply this by -4i, it's -32i squared, or positive 32. Add, that's 0. And we're done. Notice how, again, the remainder is 0. And now for the last step, we're going to divide by x minus 4i. So we'll use 4i for our synthetic division. Bring down the 3. 4i times 3 is 12i. Notice how the I terms are opposites. Gives us -2. And 4i times -2 is -8i. Again, we have a remainder of 0. So this represents our last linear factor of 3x minus 2. So this linear factor would be 3x minus 2. And the 0 of 3x minus 2 is 2/3. Add 2 to both sides and divide by 3. So the last 0 that we're looking for up here is 2/3. So by using the given complex 0 and its conjugate and analyzing the graph of the polynomial function, we were able to find most of these zeros, and then we found the last 0 by performing division using the known factors from the known zeros. So we found all 5 complex zeros of the given polynomial function, and we also found the 5 linear factors of the given polynomial function. I hope you found this helpful.